This is the first video supplement for CIS 251, Grand Valley State University's course on computer organization and assembly language. In this video, I'll be giving an overview of the course and showing how to build the simplest possible computer. One important goal of this first, somewhat long video is to provide context for the rest of the topics in this course, so that when we're studying the finer details of topics like binary or combinatorial circuits, you'll have a clear understanding of how those fine details are relevant to this course and to computer science in general. I really do understand how difficult it can be to learn something if you don't understand how you're going to use that information. Also, because this is an introductory video, and a long one at that, I've added links throughout the video that will help you skip over some of the background material that you may already know well. Although I will caution you against skipping over material where you may know the mechanics without really understanding the reasons why you're doing what you're doing. In a nutshell, this course is going to teach you how to build a simple CPU from scratch and then program it, if you were stranded on Gilligan's Island. Actually, it's more accurate to say you'll learn how to build a simple CPU if you were stranded in your grandfather's garage or some other room full of old wires, batteries, magnets, and such. The organization part of this course is how to build the simple CPU, and the assembly language part is how to program it. A CPU you build in a garage will be huge, slow, fussy, broken more often than not, and grossly inefficient. But in theory, if you are patient enough, you could get it to work. In the next course, Computer Architecture, you'll learn about the design techniques like caching and pipelining that we use in today's faster, more efficient CPUs. In other words, this course is analogous to teaching you how to build and fly a simple plane like the Wright Flyer, whereas Computer Architecture is analogous to teaching you how to build and fly a jet. We'll begin by building the simplest computer imaginable. This won't be a general purpose computer like the ones you're used to using, but rather a in this case, a blue box that can physically calculate the answer to one specific yes/no question. For example, one such box may physically calculate whether x is prime. Another could answer is x less than y. A third might answer is x plus y even. Although these boxes may seem more like toys than a useful part of the computer, we'll soon see how to combine these boxes into more and more complex devices until we have a complete CPU. The first thing we need to do is figure out how to communicate with the box. In order to make it as easy as possible to learn how the box works, we want to choose a communication method that is as easy as possible to implement. In other words, we want to keep the inside of the box as simple as possible, even if it makes the box more difficult to use. With that in mind, for now, the box is going to talk to us using a single light. If the light is on, the answer is yes, and if the light is off, the answer is no. The more interesting question is how we should talk to the box. Our desire for simplicity means that we can't use traditional input methods like keyboards, mice, microphones, and cameras. But here's an idea that is simple to implement. Let's put a set of dials labeled with the digits 0 through 9 outside the box. Users can then turn the dials to the desired numbers. For example, if I wanted to know if 43 was prime, I would turn one dial to 4, the next to 3, and then wait to see if the light came on. Well, that sounds simple enough, but can we do better? Would you agree that reducing the number of digits on each dial will simplify the device? If nothing else, it allows the mechanism that reads the positions of the dials to be less precise. Alright, so if fewer labels per dial is better, how low can we go? Well, 2. A dial with 2 labels is really just a switch. It's either on or off. Given that computers are electronic devices, I suspect you can imagine how an on-off input is much easier to handle than tracking the position of a dial, which is a more mechanical operation. Thus, having a series of on-off switches will greatly simplify the inside of our box at a cost of requiring us to transform the input we have in mind into a series of on-off switch positions. At this point, some of you may be wondering how this transformation works. How do you know how to set the switches to ask the box about the integer or other input you have in mind? The short answer is, it's arbitrary. Whoever designs the box gets to define the meaning of each combination of switch positions. For example, given 3 switches, I could decide that setting all the switches off represents 14, setting the first 2 off and the third one on represents 33, and so on. Such arbitrary assignments are completely legitimate, but aren't very common and are only useful in very special circumstances. So although we can arbitrarily assign integers to switch positions, it's much more common to label the switches with a 0 and a 1 instead of off and on, and then interpret the switch positions as a base 2 or binary number. I'll be using binary for the rest of the video. It's okay if you don't already know binary. You can pretend that I'm using a completely arbitrary mapping, because the mapping doesn't really affect any of the key points in the video. However, if not knowing binary is going to bug you, you can skip ahead to my 3rd, 4th, and 5th videos, which discuss binary and related topics. So here's where we are. We have an empty blue box with 1 light for output, 3 switches for input, and a map of switch positions to integers that tells us what the input means. The next thing we need to do is specify precisely what the box should do. English phrases like x is prime or x is less than y are useful for conversing, but to build a computer, we need to be much more precise. After all, this is why we program computers with programming languages rather than prose. So what is a precise, mathematical, programming language-like way we can specify what this blue box is supposed to do? One technique is to create a table that lists the output for each input. This table is called a truth table. Here we have a truth table for the box that determines if a number is prime. I'm going to start calling this box a circuit, since that's the more common term. We're going to see how this truth table tells us exactly how to build the circuit. Or in other words, what gadgets to put in the box and how to connect them. Here again we have the truth table for the is prime circuit we're building. Under what conditions should this circuit output a 1? Well, since the purpose of the circuit is to identify prime numbers, the output should be a 1 when the input is either 2, 3, 5, or 7. These are the only input values that are prime. Remember, however, the hardware itself doesn't assign any meaning to the input values. It doesn't think in terms of integers, it just sees a bunch of zeros and ones coming out of the switches. So, how do you describe in terms of the inputs when the output should be a 1? Well, the output should be 1 if A is 0 and B is 1 and C is 0, which means the input is 2, or A is 0 and B is 1 and C is 1, which means the input is 3, or A is 1 and B is 0 and C is 1, or A is 1 and B is 1 and C is 1. If any of the above conditions are met, then the input represents a prime number and the output should be 1. Otherwise, the input does not represent a prime number and the output should be 0. For reasons that will become apparent soon, I'm going to replace the phrase 0 with is not 1. So with that in mind, what are the key words in the statement? Well, and, or, and not. If we can build physical devices to represent the key ideas of and, or, and not, then we have an algorithm for turning a truth table into a physical device that can compute something. Inside our blue box, each switch is connected to a wire. If the switch is in the 1 position, there's an electric signal on the wire. If the position of the switch is 0, there's no signal on the wire. This is analogous to turning a switch on, which sends current through the wire to the light. The current is, in some sense, the signal. Turning the light off removes the current, causing the light to go out. A NOT gate is a physical device that flips the state of a wire. If the wire going into the NOT gate has state 1, in other words, has a signal, then the wire coming out of the NOT gate will have state 0, will have no signal. Similarly, if the wire going into a NOT gate is 0, then the wire coming out will be a 1. I'll discuss how to build such a device in the next video. For now, just treat the NOT gate as a magic box that we can use to build circuits. Here's another, somewhat unconventional way of looking at a circuit. You can pretend that each wire in the circuit is making a claim, and the signal on the wire tells us whether that claim is true or false. The wires attached to the inputs make the claim the input is set to 1. In the case of input A, this claim is true, as indicated by the signal on the wire. In the case of input B, this claim is false, as indicated by the lack of a signal on the wire. The wire attached to the output of a NOT gate makes the opposite claim of the input wire. In this case, the output of the top NOT gate makes the claim that input A is not 1, which would sound like not input A equals 1 if you were to write it in Java or C. This claim is false since input A is in fact set to 1. Likewise, the output of the bottom NOT gate makes the claim that input B is not 1, which, in this case, is true because input B is set to 0. Although its name is fairly descriptive, the behavior of a NOT gate is formally specified with a truth table that lists what the output should be for each possible input. A NOT gate always has exactly 1 input and 1 output. The next thing we need is a physical device corresponding to the concept of AND. We call this an AND gate. What else would we call it? Anyway, AND gates behave just as the name suggests. The output wire makes the claim that all of the input wires are true. Input 1 is true, and input 2 is true, and input 3 is true, and so on. Here we see the 4 possible scenarios for a 2-input AND gate. Notice the output is true only when both inputs are true. As with a NOT gate, the behavior of an AND gate is formally specified by a truth table. Unlike a NOT gate, however, an AND gate can have any number of inputs. Regardless of the number of inputs, the output is true only when every input is true. Okay, one piece left, OR. Just like the AND gate, the OR gate is fairly intuitive. Its output wire makes the claim that one or more of its inputs is true. Input 1 is true, or input 2 is true, or input 3 is true, and so on. Again, we see here the 4 possible scenarios for a 2-input OR gate. Notice the output is true whenever at least one of the inputs is true. Another way to say this is the output is false only when all the inputs are false. Descriptive name notwithstanding, the OR gate's behavior is formally specified by a truth table. And, like the AND gate, it can take any number of inputs. In all cases, the output is true if any one of the inputs is true. Or, in other words, an OR gate produces a false output only when all of its inputs are false. We now have the 3 building blocks we need to construct our circuit. There are other possible gates, but since we don't need them, we'll discuss them later. Let's go back to the truth table for the is prime circuit and the statement describing it. This statement, written in terms of AND, OR, and NOT, our 3 building blocks, tells us exactly how to put these building blocks together to build our circuit. Before we begin, notice this statement is equivalent to making this claim. The integer represented by inputs A, B, and C is prime. Here's a diagram showing how to build the is prime circuit. First, notice that the wires are connected only where there's a dot. If there isn't a dot, then the wires pass over or under each other without connecting. Now, let's look at the claim each wire makes. The horizontal wires at the top make claims about the values of the inputs. The very top wire claims that input A is 1, whereas the NOT gate means that the second wire from the top is claiming that A is 0. And likewise for the other 4 horizontal wires. The wires coming out of the AND gates make claims about the value of all 3 inputs together. For example, the output of the leftmost AND gate claims that input A is 0, and input B is 1, and input C is 0. To see the justification for these claims, notice which horizontal wire each vertical wire is connected to. Remember, in our truth table, we decided that the input 0, 1, 0 represented the integer 2. Thus, the output of the leftmost AND gate is effectively telling us whether the user entered 2 as input. Similarly, the other 3 AND gates tell us whether the input was 3, 5, or 7, respectively. The OR gate tells us whether any of the 3 AND gates is true. Thus, it tells us whether the input is 2, 3, 5, or 7. These are the 4 prime numbers in our input range of 0 to 7. Thus, recognizing that the input is one of these 4 values is the same as determining whether or not the input is prime, which is exactly what the circuit is supposed to do. There you have it, a physical device that determines whether an integer between 0 and 7 is prime. You can build a physical box to answer any yes-no question in a similar way. Well, actually, first I have to show you how to build AND, OR, and NOT gates. That's the subject of the next video. Also, notice the circuit we just built has 3 input switches. Video 3 will discuss how you know how many switches you need. Video 4 discusses binary, the standard mapping between switch positions and integers. And then Video 5 extends the idea of binary to hexadecimal and other number bases. Let's finish up by looking at our circuit in a digital logic simulator called JLS. This simulator will allow us to experiment with different inputs and take a closer look at how the signals travel through the circuit. JLS is a free program written in Java, so feel free to download your own copy and follow along. So here we have the is prime circuit. It's the same implementation we just saw a minute ago, but the inputs and outputs are slightly different. Instead of using switches, our outputs are simply wires. These wires are given their values outside the circuit in much the same way that function parameters in a programming language get their values from the calling function. This function-like model for circuits allows us to compose the circuits into more and more complex devices in the same way we compose programming language functions to build more and more complex programs. The input to this circuit appears
on the input pin on the left. The blue ribbon at the top tells us that this is a 3-bit input pin. That means, although the input is presented logically as a single item, it's really 3 pins grouped together. The wire coming out of this input pin is really 3 wires bundled together. We create these bundles for the same reason we use arrays in programming languages. It allows us to package our data together and make it easier to manage. For example, it saves us the trouble of having to make 3 copies of everything or drag 3 parallel wires around the circuit. Coming off of this 3-bit bus are 2 output devices labeled binary and decimal. They aren't part of a real circuit, they're just debugging tools that I've added here for convenience. Now we come to the unbundler. At this point, we want to treat each of the 3 input bits separately. So we use the unbundler to pull apart that bundle of 3 wires into individual wires. You'll notice that I've crossed the wires coming out of the unbundler. This crossing doesn't have any special significance. I just wanted to put the most significant input bit at the top and the least significant input bit at the bottom so that this diagram was consistent with the one we were looking at earlier. Flipping the bits as I did here doesn't have any effect on how the circuit works. It just allows us to read the input top to bottom. And then from this point, everything else is identical to the diagram we were looking at earlier. So let's begin by watching how the circuit handles an input of 3. So I'm going to edit the signal generator so that it puts a value of 3 on the input pin. The signal generator is also a debugging tool for the simulator. It's not part of a real circuit. So I'm now going to run the simulator, and we see how the values propagate through the circuit. The first thing you see is the display boxes showing us the values on the wire coming out of the input pin. We ask that the input be 3, and the decimal window says it's in fact 3, and then we can see that that's encoded in binary as 011. The 011 is what's on the wires. Those 3 wires get unbundled. The first digit, input A, is sent to the top set of wires here. And this is why I crossed the wires coming out of the unbundler. Since input A is on the left over here in the truth table, I wanted it to be on top here in the circuit. I find it easier to follow that way. The very top wire tells us whether input A is 1. It's not, therefore this top wire is black. The second wire down here is connected to a NOT gate, so it is telling us whether input A is 0. And input A is in fact 0, hence the wire is red. The next 2 groups of wires handle inputs B and C. As before, each AND gate is looking for a specific input. The leftmost AND gate is looking for the input 2. In other words, it's looking for A to be 0. Or if you prefer, it's looking for not A to be true. It's also looking for B to be 1, and it's looking for C to be 0. This isn't the case because, as you can see here, C is 1 and not 0. So the output of this AND gate is false, indicated by the black wire. The second AND gate is looking for the input 3, for A to be 0, for B to be 1, and for C to be 1. And this is the case, as we can see, because the 3 inputs into this AND gate here are all red. So if the 3 inputs are all true, then the output is true, hence the red wire down here. And then the last 2 gates are looking to see if the input is 5 or 7, and it's not, so the outputs are false. Remember, the circuit is looking to see if the input is one of the 4 inputs for which we want to return 1, 2, 3, 5, or 7, the prime numbers in our input range. The OR gate is looking to see if we have found at least one of those inputs. In this case, we have 3. Since at least one of its inputs is true, the OR gate produces a true as output, so our circuit gives us the 1 that we're expecting. Therefore, it says, yes, 3 is prime. Okay, so now let's see what happens when we change the input to 4. So again, I'll modify the circuit generator here. And I will rerun the simulator. And we can see we've changed our input. It's a decimal 4 or the binary 100. Now, the binary value for 4 doesn't match the inputs for any of the AND gates. For any of the AND gates, at least one of the inputs is false because that bit doesn't line up. Therefore, all of the AND gates generate a false, right? None of them are looking for the input of 4, so all of the inputs to the OR gate are false, so its output is false. So in effect, the circuit is saying no, 4 is not a prime number, which is what we'd expect. So at this point, I'd encourage you to download JLS, download a copy of this circuit, which I'll make available on my website, and try it out for yourself. Try different inputs, try moving the wires around, and see if you get a feel for how this works. This algorithm for generating circuits from truth tables follows a fairly straightforward pattern. Let's look at this file. Notice that the truth table is empty. There aren't any output values specified, and none of the wires are connected. There aren't any dots in here. These wires all cross over and under each other. We haven't specified a circuit yet. We just have a template for generating a circuit. Let's build a circuit to determine whether x is a multiple of 3. We'll begin by filling out the truth table. Now, we don't actually need to modify the truth table to make this circuit or JLS work. I just did it for clarity, so we have a reference to what we're doing. Now we need to connect the wires so that the AND gates here will match the inputs that are supposed to be multiples of 3, 0, 3, 6, 9, and so on. So let's see. Our first input that's a multiple of 3 is 0, 0, 0, 0, 0. So we'll connect the wires accordingly. 0, 0, 0, and 0. The next input that's a multiple of 3 is 3, 0, 0, 1, 1. So we'll do that here. We'll do 0, 0, 1, 1. And the next one is 6, 0, 1, 1, 0. 0, 1, 1, 0. And there's 3 more, 9, 12, and 15, which I will skip ahead and do. Okay, good. Now we need to connect the AND gates we're using. Notice our template has 8 AND gates. Think a minute why I picked 8, but we only need 6 of them. So we need to wire up or connect the 6 AND gates that we actually used. All right, so let's see if it works. Let's put 0 on our signal generator and run the circuit, and it says here the output value is 1. 0 is a multiple of 3. All right, so let's try, how about 6? 6 is also a multiple of 3. Run the simulator. Our output is 1. Yes, because 6 is a multiple of 3. Let's try 7. 7 is not a multiple of 3, so we get a 0 like we expect. So it appears that the circuit works. So now you know how to build a simple computing device given 3 basic gates. So if I were to come and give you a whole pile of AND or a NOT gates, you could build an actual physical device by doing what we just did right here. You would lay out the gates in a wire like a grid, and then connect the wires together to make the AND gates look for the inputs corresponding to an output of 1. It turns out you can buy computer chips with a pattern just like this. They are called programmable logic arrays, or PLAs. They are the same grid of gates and wires. And you can then use a tool to make the desired connections so the chip implements the desired circuit. Actually, I've heard it works the other way. The chip comes with all the connections already made, and then you break the connections you don't want by blowing tiny fuses. Apparently, it's easier at that small scale to break things than to create them. I like to call this technique we use today the big hammer technique. It approaches circuit design by taking the problem and smashing it with a really big hammer. This technique is neither elegant nor efficient, but it works. This isn't the best way to design most circuits. In fact, we'll soon encounter circuits that are too large and complex to be built in practice using this big hammer technique. In theory, of course, you can build the circuits because it works for any circuit, but in reality, it's just not practical. The focus of this video was to give you an approach to building computers that you can get your head around in about 30 minutes. I hope you have a sense, an intuitive sense, that if I were to dump a bunch of and, or, and not gates in your lap, you could connect them together and build a computer, or at least most of a computer. Of course, you wouldn't really want to build a computer this way, but I think it's a great starting point to have the confidence that you could do it, given enough time and patience. So let me finish by giving you a couple of things to think about. One, how could you extend this technique we've been looking at to circuits that aren't just yes-no answers, to a circuit that may give you an answer that requires 2 bits, 3 bits, or 4 bits? The other thing to think about is, how about a circuit that uses 2 different variables? For example, like, is x less than y? How would you build a circuit that could tell you if a 2-bit value of x is less than some other 2-bit value of y? Try that out, see where you can get. And thanks for watching.